All right, guys, welcome to another episode of RoboPapers. Super glad today to have Arnav, Vib, and Gokul. They are authors of this paper called A Smooth Sea Never Made a Skilled Sailor, a robust imitation via learning to search. Thank you so much for making the time, guys. Maybe, as a start, you guys can go around and share a little bit about yourself. Maybe Gokul, you can start.
Oh, yeah, sure. My name is Gokul. I am a last year PhD student at the Robotics Institute at Carnegie Mellon. Yeah, it's been a lot of fun working on this stuff.
All right, cool. And
Yeah,
Arnav?
I'm Vibhakar, and I recently graduated from Carnegie Mellon with a master's in robotics, and I've been working in the AV industry for the past year, and happy to be on this podcast.
I'm Arnav. I'm based in Montreal in Canada. I'm a PhD student at Miller. And before this, I spent a few years at Microsoft. And before that, I did a master's and bachelor's in mathematics.
Awesome. Yeah. All right. Thank you for the quick intro. So if one of you can shout sharing screen, and then we can just go dive straight in.
Okay. So thanks for having us here. I'll first give a brief overview of our method, Sailor, in the paper titled A Smooth Sea Never Made a Skilled Sailor. This was a joint collaboration between Mela, CMU, and Cornell. Me, Web, and Gokul are here in the presentation. So right now, it's an exciting time for robotics in the world. Like if you see around a lot of demonstrations, a lot of videos made by Pi or even Gemini, Google team and all, you see like they are able to do quite complex manipulation tasks. And if you ask what drives that frontier of imitation learning for robotics today, it can be broken down into two things. The first is you have to collect a lot of data. There has to be a lot of demonstrations collected maybe using teleoperation, or you have a human in the loop actually giving you the data set. And the second thing is you need very powerful models. In the recent era, it has been about using diffusion policies, which takes an observation. And based on the observation, there is an encoder that is used to encode high dimensional things like images and proprioceptive states. And the goal is to predict a set of actions. For example, if you see on the right hand side here, the agent takes this observation on the left and predicts a chunk of action for 1 second or 2 seconds, which is denoted by a blue line. Now, this has been pretty successful in most of the developments in robotics in the recent times, and we see a lot of things coming out by different companies. But is that it? Is this the answer to everything, that just collect a lot of demonstrations and do behavior cloning with a very powerful policy? Let's take a step back and think about what happened with LLMs. So we had a long pre-training done with a large text corpus where the goal was to predict the next token, and it was not enough. We had to do some form of RL and test time scaling after to make it much better at the tasks that we care about, like math or coding and all. So even in the context of LLMs, just doing behavior cloning was not enough. LLMs are a deterministic system in general, whereas robotics are a much harder problem to solve because there is embodiment, there is stochasticity, and other factors. There's environment, and it's also about safety. So it becomes a much harder problem to do it for robotics. So one of the question is what should we do to actually go beyond behavior cloning? And to answer this, another thing is, what if we just have the same set of demos that we collected so far and have no extra or more human interaction? And how could we teach the agent to recover from mistakes? So for this led to the idea called Sailor, and Sailor stands for Searching Across Imagined Latents Online for Recovery. And I'll give a brief overview of the algorithm. Now, as the first step, we collect a bunch of demonstrations, and on the demonstrations, we contain a policy based on behavior cloning. In this work, we use the diffusion policy. Now, after training the diffusion policy, if I just directly deploy that diffusion policy, you can see the set of actions by the purple dots. It actually won't pick up the object. It makes some mistakes at test time. And this can often happen if the agent goes out of distribution. That means that it goes to a state it has not seen before, and it does not do what to do there, which is why mistakes happen. And there is no way a behavior cloning or a models trained with diffusion policies can fix this directly. As you can see, the agent doesn't pick up the object. So instead, we propose you take this base actions that was generated by the diffusion policy, and you have a pre-trained world model. You can actually do a local search in the latent space of the world model to predict the set of residuals. And doing this local search gives you some set of actions to collect the actions generated by the base policy, which we also call the base actions. And when actually you deploy this, the corrected actions when deployed in the environment was able to like pick up the object, which means Sailor was with a learned reward model and a world model was able to like refine the base actions with residual actions in a way that it was able to avoid failure. And while training, you can do this additional step called distillation, where when after doing the replanning thing, you can always like improve your base policy with that and keep doing this loop. I'll jump into this in more detail now. So overall inside the tech, there are like 4 components. The first, as I said, is the base policy, which is like trained with the expert demonstrations. And the second is the world model. And the third is the reward model. And then we have the plan. Now let's look into this one by one. So the goal of the base policy, as mentioned earlier, is to propose base actions. So in order for to plan successfully, we need like 2 things. We need a world model that can actually tell you, given a set of actions, where the agent will end in. And we need a reward model that can evaluate the set of actions. And then combining the world model and the reward model, we can fit this into a planning process that search for the best future outcomes using these 2 components. So the first component is the base policy. So for base policy, we directly use the diffusion policy, and it just gives us a chunk of actions for an observation. And this is trained with behavior cloning loss over the set of expert demonstrations that we collect at the start. Note that the expert demonstrations, once we have received at the start of training, is always fixed. We do not add any extra human data after training. We use diffusion policy in this work, but of course, this can be extended with like a VLA or even more powerful models that come out. And why diffusion policy, someone would ask? Because robotic data, in a way, is many a times like multimodal. And diffusion process is able to like capture this like pretty well and has been like successful at a wide range of real world tasks, which is why we like experimented with diffusion policy in this work. The second component is the world model, right? Because once you have a sequence of actions and you want to look for maybe an improved sequence of actions, given a candidate set of actions, you cannot like do planning in the real world because the world is often like dangerous and unsafe, and you can't just go around and try everything out you want. And this was the motivation behind using the world model that allows the agent in this work to predict the consequence of a set of actions. Now, one thing I would like to note here is for the world model training, we did hybrid training where we trained the world model on both the mixture of expert demonstrations and the on policy rollouts. We would like to highlight that this was important because you want the world model to be good at both on expert visited states and the on policy data to be good at planning. And in this work, we of course like trained the Dreamer world model from scratch. But of course, the model is not limited to just this world model because we propose a framework. It can use any other form of world model like TDMPC, foundational world model trained on a lot of data. And as we saw today, like maybe Genie 3 can be used instead too.
Yeah. I was just gonna say this is just updated today, probably.
Yeah.
Very cool. Okay.
So the first part is you train the world model. And why use a Dreamer world model in this work? So you train the world model. What Dreamer does is it allows planning in the latent space, which is like pretty important because we want to do MPPI, and because you are generating a bunch of actions and you want to evaluate everything together. Planning in the latent space allows you to fit everything on a single GPU. It's very memory efficient and fast. It doesn't lead to a lot of latency in general. That's why we used the Dreamer world model. Another reason was its success in like visual tasks in general on Atari and even on robotics as shown in D3. The third component is the reward model. Because we are doing learning from demonstrations, we don't have the ground truth reward function or the successful or the failure cases or the condition on the rollouts that the model generates. So we need a way to evaluate how good the states visited by the agent is in general for planning. And for this, we propose training a reward model as it was done in the moment matching paper, where you try to maximize the divergence between the state visited by the expert and the state visited by the agent. And as I said earlier, it's just like a classifier that actually tells if the state belongs to the expert or the likeliness of the state visited by the expert. Now, we train this reward model on the latent or the imagined latent space of the world model. And because of this, it allowed for like efficient evaluation again during planning, because we were doing rollouts within the world model. And now because we can just use the latents, to get the reward outputs. Now, also because in planning, we have this thing of we can only plan till like some horizon h. So to account for anything after that, the states visited or after h states, we also train a critic network, which is trained to predict the expected rewards beyond the horizon. So to summarize, for the base policy, we have a diffusion policy which generates some chunk of k actions. We have a world model, which given a set of actions can predict the outcomes or the states that the agent will visit in the future. And we have a reward model, which predicts the export likeliness of the future outcome. That it evaluates if this set of actions taken by the agent or the candidate set of actions are good or bad. And then we use these three components within the planner, where the goal of the planner is to generate a set of residual actions on top of this base actions. And it like optimizes this like optimization problem as shown below, where you want to like account for the n step returns and it find the best residual action plan that maximizes this within the world model. So putting it all together, again, the first is we get a current observation. Using the base policy, we actually get the base action plan. Now this, with a set of sampled actions coming from the MPPI planner, gets fed to the world model. Now, the world model and the reward model helps you evaluate each of the n action plans that are here. You can get the Q values of those. And now you select top K, which is we select around top 10% of those actions, and then update the parameters of the MPPI, that is the mean and the standard deviation, and do a replanning for K iterations. And after the last iteration, we just select sample one of the actions and then execute one action or a few actions in the environment and then replan again. So this was the inference pipeline, but there were like three important phases of training that went into training this like C-worthy algorithm. The first is the warm start. Now, once we have trained the diffusion policy, we do a long set of generation of rollouts from this base policy in the environment. Now, as I mentioned earlier, we trained the world model from scratch. With this lot of data set collected from the base policy in the environment and the expert demonstrations, we actually train the world model and the reward model for a warm start process. The second is once the warm start is done, we do the online fine tuning, which is very similar to a batch online RL. That is, for a set of states in the replay buffer, we relabel them back. We relabel with the planner. We update. We distill that back to the base policy. Then we collect more data, update the world model and the reward model and the critic, and do this like iterative tuning. Now this makes it an export iteration framework because the refined plans are always like distilled back to the base policy. And I want to highlight that this was important because with training, you also want to improve the base policy that was that we start from what we started with. And for the distillation, we just relabeled data using the MPPI planner and do the normal behavior cloning for this. Now, the results. The first thing is, here we can see that on the left is the video of the diffusion policy. On the right is in the middle is the video of the Sailor agent, which was able to solve the tasks. On the right hand side, we actually tested Sailor with like Sailor and both the diffusion policy for different set of expert demonstrations or different size of expert demonstrations. We see that with like less number of expert demonstrations, the performance of the diffusion policy is pretty is less than like 30%, whereas Sailor is able to like recover close to what it achieves with even with 100 demonstrations. And at the same time, you can see that the performance of DP increases a lot, whereas Sailor, just by learning with the same set of expert demonstrations, not having the reward model information, and doing this form of test time planning is able to like outperform diffusion policies. In some more tasks, this is the nut assembly round task, where the agent has to pick up the peg and place it in the silver thing. And we see that with 25 demonstrations, the performance of diffusion policy is pretty bad. It's just like 20%. Whereas Sailor is able to like reach 87% with the test time planning and updating the like learning a world model, reward model, and the export iteration framework. Another task is
Sorry, I have a quick question. So it seems to me that Sailor is already doing really well with very, very little data. So does that mean the world model and reward model already like captures most of what you want, like at pretty low expert demonstration? Is that what you're saying?
That's a great question. So So the thing is, yeah, you're right. So for good planning, we actually want a good world model and the reward model.
Mhm.
Now, for training the world model, we did the hybrid training. And hybrid training was based on both the expert demonstrations and the on-policy data.
Mhm.
And we actually, when we want to do test time planning, we actually want the agent to be good at these two things. Both the things, like maybe what the expert does and also like where the policy visits. And we want the reward model to be well differentiated on those things. Now,
Mhm.
because once we have that, we can just like do the planning with like states visited by the agent. We can generate the actions from the base policy and do the test time planning and improve with the residual actions.
Yeah, and I guess maybe like to build off what Arnav was saying there, like I think for a lot of problems, right, learning a good reward model takes a lot less data than you might expect, right? In some sense, I just have to like verify rather than generate, so this should take kind of less data to learn. So I think like maybe like the kind of underlying kind of math reason for a lot of the kind of stuff here and in some of the other results, I guess, is just that like you should need less data if you just have to learn like if something's good or bad versus how to do the whole thing in the first place.
Got it. I saw your other paper, the generation verifier gap thing.
Oh,
Maybe
nice.
that's what you're talking about. But how about the world model? I would have imagined maybe the world model takes a lot more to build this world model, is it not? I mean, you mentioned Genie, Genie 3 stuff. So, like, how much does a good world model you think help with
Yeah.
just having like, let's say maybe lock out the part with just a couple of demonstration or
Yeah, it's a good question, right? I guess maybe I would think that like you probably want like, you know, some like kind of base knowledge of like the way the world works or like physics or things like this, right? One hopes that, you know, if you aren't trained this from scratch, maybe pre-training gives you a bunch of that, right? Then maybe for like the sort of fine-tuning process, you might want to actually make sure you kind of like Arnav was saying, you both can do kind of predict what happens when you do the right thing, aka what the expert did, and predict that the kind of wrong thing happens when you do what the learner did if it was like a mistake, something like this, right? So I don't think it should require like a sort of a crazy amount of data to do that, right? I think if you have some sort of like kind of good set of like base knowledge of physics, it shouldn't require too much fine-tuning. I think the other thing that's true is that like training a world model is just sort of supervised learning, right? So I can kind of just shovel whatever data I have into this world model generally, right? So like I can put in, I don't know, suboptimal data if I screw up and I'm demonstrating things, or maybe I have multitask data or play data, and I can kind of shovel all of that in, right? So I guess I think of them as almost like a sponge that can take a lot of data. So yes, I think in general, they do require data. But I feel like given it's data that's relatively easy to get, unlike like perfect expert demonstrations, I feel like it's not the worst thing in the world, you know?
Well, that does depend a little bit on how granular the problem is, right? Like you still have to get into the interesting, it has the same interesting exploration problems that you would get with your rollouts, right? Like what if I want to do like screwing a bolt on, right? I'm not going to get all the little variations there maybe. Or that might be, one could argue that would be an equally comparative difficult problem. What do you think? I see.
Yeah, Vib, do you want to take it?
Yeah. So I think one thing to note here is these world models are like task specific.
Gotcha.
So that is the reason why you see them being trained by less amounts of data than something like Genie 3. But like as you said, if you want to actually get into like fine grained stuff, you need like a much more powerful world model. And luckily we have a lot of world models available online, which are pre-trained on tons and tons of data. So what you would expect is you take any of the pre-trained world models and then you fine-tune it for like a set of tasks. And we expect it to kind of generalize in terms of physics and also in terms of like contact. Yeah, if the pre-trained world model is not good, then it won't be able to do it. And we would need demonstrations showing how the physics of screwing something works.
Sure.
But in general, if we have good pre-training, we should be fine.
Also, like, I would like to add one more thing here. Yeah, so for world models is also like, as you said, like if you want to do like more granular task of like putting the bolt on and on, once the policy like fails around that state, right? And then you will collect more data using the on policy rollouts. So around that region, you are going to improve the world model in the batch online learning. And maybe if you have trained a reward model that actually like differentiates between what is a good action and what is a bad action, like what would lead to like fitting it perfectly or messing it up, you can actually like, even if the policy goes there again, you would be able to differentiate which action to take And in a way, like you can improve with that. So the world model has to be also like locally good around like what the policy visits and the expert visits.
Yeah, like maybe to summarize both Vib and Arnav's points, it's like either you have to get it in the pre-training, right, or you have to get it in the online fine-tuning, right? Maybe there's like no free lunch other than those
Yeah.
two. I guess you hope you get as much as you can in the pre-training, and then for the rest, you know, you kind of have to online see what happens.
Yeah, makes sense. How much data did you end up once you add in the data from the online training? Like, how much data do you end up using to train a policy with Sailor?
Yeah, so I think that depends a lot on the task. For like very easy tasks, door is like a very easy task where you just have to open the door. I think we had like around 100 to 150 total demonstrations for like opening the door. And for harder tasks, like where you saw like 2 pick and place, so I think there we needed more in the order of 200 to 300 like rollouts of the model to complete the
Makes
training.
sense. Yeah, makes sense.
See, Arnav, you wanna go ahead with the
Yeah.
presentation?
Also, just feel free to just like ask us more questions. You know, like
Yeah, sure. Okay, one other question on that line. So,
Okay.
So you have 200 to 300 demos. Did you try just like taking the top N% of those demos and training diffusion policy on it? How does that end up being better or worse? I assume worse. Or
So one other thing is, for RoboMimic tasks, all the demonstrations that are collected, which was in the dataset, was already pretty good. And we actually like checked went through few of them. It was like of good quality. And it was hard to like segregate which demo is good and bad. For the other tasks that we have in the paper, like from RoboSuite and the Maniscal, we actually collected our own demos and ensured that each demo is actually good. And we just already discarded all the demonstrations, which was maybe pretty long or had some issues. So we actually like ensured the demonstrations are of good quality from the start.
Yeah. Also, to add on to that, I think you mentioned like if you train in the 200 to 300 demos, just the top K. So we actually don't have action labels for those because it's just like rollouts of the policy, and we don't have access to any expert to relabel failed trajectories, and we don't even have a notion of success of those trajectories. So we can't train on the data that we collect on policy directly, like for behavioral learning.
okay, fair enough. Yeah.
Yeah, like, I think right, exactly like Bib's saying, right? It's like given we don't have like a reward function, right? Kind of like how do you pick the top N%, right? That said, I guess I think maybe a different way of thinking about your question is like, okay, let's say I just did a bajillion rollouts. I like scored them all with the reward model and I got like some set of things. Can I basically then just like pick the best of them and like, you know, train the policy on that, right? I think that maybe gets into some sort of like deeper questions about like, you know, what is the value of test time planning versus like learning a policy and stuff like that, which like, you know, yeah, we're happy to talk about that. But like, I think, yeah, it's a good question.
Yeah, fair enough. Okay.
Arnav, you want to keep flipping through slides?
Yeah. So in the task of Do, it was pretty interesting that we were able to solve the task with only a single demonstration, where a diffusion policy is just less than 10%, and the sailor was able to like successfully solve the task with just online interactions. And there are like more tasks like Poke Cube, which was another task of Maniscal, where also like with increasing the demonstrations for diffusion policy, it shows improvement, but sailor is able to like consistently perform even with like less data. Now this is one of the coolest visualizations.
This is also my favorite part.
Yeah.
This is our favorite part from the paper. So we talked about like learning a reward model because we don't have access to the ground truth information, or if we collect on policy data, we don't know if it was successful or a failed trajectory. And we want the model to recover from that. So we wanted to also see like what is actually how is this learned reward model helping at test time. So as you can see here in the first phase, we actually like deployed the diffusion policy. We used the reward model that was trained for the sailor agent and actually plot this down for the diffusion policy with respect to time as the agent moves. So this is on the y-axis is the value that was obtained by the reward model for the diffusion policy. Now, as you can see, diffusion policy fails because of many reasons, like going to OD states and all. It missed like hanging the peg. Now, what we did, we actually like reset the policy to one of these states where the diffusion policy was getting stuck and all. And we just like rolled out the sailor agent from there. And we could see that with test time planning on the same diffusion policy, it was able to like solve the tasks. successfully. And also this is visible within the reward model, that the state that was visited was like ranked high under the reward model. So in this, like, we show two things. The first thing is like Sailor was able to recover from the mistakes with test time planning that the behavior cloning or the diffusion policy makes. At the same time, it shows that the reward model is learning something meaningful here. It is able to differentiate between the failed trajectories and the successful trajectories, which is what we expect to learn.
Yeah.
Sorry. Sorry.
Yeah.
Yeah, go
You're
ahead.
saying
Go ahead.
something?
Yeah, I was going to ask a question, but yeah, you go ahead first.
I wanted to add another point to the previous slide. So one interesting observation you could see if you could go to the previous slide is like when you see the expert reward model, the Sailor reward model, you see two peaks, and those are actually the two crucial points of doing this task, which are just learned using the demos. So the first one is actually picking up the thing, and the second one is actually inserting it into the circular thing. So you see that just by learning a reward model, you are able to point out these two crucial parts of the rollout.
Yeah, I was actually gonna ask the opposite side of the question. I was curious about, when the reward model like gets a very low score, let's say, I don't know whether you can just pause that video like where I mean is a reverse true, meaning when let's see where you have
I think
You
it
know
should
when-
be somewhere around here.
Yeah.
Yeah.
I think what's happening here is it's going out of the camera frame, where it's going kind of out of a lot of things we saw in the demos. So it's like, this
Oh.
is bad, right? So I think it's maybe doing just like, this is an OOD state more than like something super deep in that sense.
Okay, got it. I see.
Makes sense.
Because I was wondering whether we can use it the other way. Say, hey, maybe you call in Sailor like more, or you use the sample more whenever your RM, give you a really low value. But I wonder whether there could be it could be used that way, or maybe this is just maybe the way to solve the problem is to go away from a minimal local local minima, and then come back, and this is how we solve it.
Yeah. It's a good
Right.
question. Yeah. Like, I guess like in some sense, right? Like, I think we're doing it's like a fixed amount of planning, like every state and every place we end up, right? But I could imagine something like what you suggest would be really useful for maybe like a more adaptive allocation of compute. So I could imagine that you say like, okay, maybe the base policies score under the RM is like really not good. But maybe we basically want to keep sampling and keep running MPPI until we basically get a higher score on it, right? And that could be like a nice way to sort of only use as much compute as you need. I think it might be hard to get like super detailed values from these reward models about like maybe this exact threshold corresponds to good or bad. I think you might need to structure it a little bit more for that to happen. But I feel like at a high level, I could imagine that sort of thing is useful for like figuring out essentially how much to plan in some sense.
And anyway, the way this reward model is learned right now is just kind of like a classify between, okay, this is what the human expert do, and this is probably not the human expert. That's what it's doing, right? Okay. So it also depends a fair bit of who are the human expert. I mean, you collect a sample of me playing football versus Lionel Messi. I think you learn slightly different things,
Yeah. I mean, we don't know how good you are at football, but I guess as much.
Come on, yeah, but sure, yeah. Okay, got it. Okay, that makes sense.
But I think that's also like an interesting point in the sense that like beyond just maybe like classifying expert versus not expert, you could imagine maybe doing something like, I don't know, using like a VLM as like a word model or something, right? And maybe that can give you sort of more like either like nuanced information about like, is this the same thing roughly speaking, or is this like meaningfully different in some way? Like, did you like drop an object? Did you like pick up a fork by the wrong part of the fork? Something like this. So yeah, I think of like when you kind of want to do like, I guess for a lot of these tasks, it was like, I think just expert versus not expert was enough, but I can imagine for like harder, like open world kind of things, then maybe you want to sort of have a kind of reward model that is essentially, at least trained a little bit to tell expert is good, other things are bad, but also has maybe some sort of common sense priors about other things that might be useful.
Yeah, I was curious about that. So you guys are doing expert versus non-expert, but like a lot of other reward learning stuff that has come out recently has been doing progress metrics or something similar to that. What do you think is the difference between the two as far as like, do you think a progress metric is less suitable for these kinds of tasks, or that like requires just more arduous data collection requirements? Are there advantages and disadvantages?
Yeah, that's a good question. Like, I mean, there's like the sort of, I guess, the usual limitations of progress metrics, right? Like, if the task is like periodic or something, it might not work out the way you want it to.
Yeah.
But I guess and this is like a little in the weeds, but like I think of a progress metric as kind of more like a queue function in the sense that it kind of tells you like kind of what will happen after this, versus like we're kind of learning like a reward function in the sense it tells you after you did something how good this was, right? And a lot of times I think like learning queue functions from data is kind of hard in the sense you sort of need more data to do it. Like the paper about the generation verification gaps that Michael was mentioning was essentially making this point. So I think that like, I think if you can get enough data to do it well, I think it makes sense. But I think you have to, one, deal with these limitations about like periodic tests, and two, I think you have to also like, it's not super clear to me if you can just shovel like arbitrary data into like a progress metric thing and see it like kind of always be reasonable, right? Like if we also put, someone who's really bad at football playing football and we like try to use that progress metric, might not do what we want, right? So I think it depends a little bit on the details there.
Yeah, fair. That's a good answer.
One other point I want to add is like, even you can train a progress metric and all, but it again like involves maybe some form of inductive biases that are added while training that. Whereas here we are not making any such assumptions and just training to like differentiate between the expert and the on policy so that it can figure out with this classification where it makes the mistakes. Like as Webb pointed out, the bumps, maybe at aligning the peg or like placing it in the right position and all, and it can just improve on that. So with this like reward model, it's able to like figure out where it's currently bad at compared to the expert, first improve that and then keep on improving over time.
Yeah, to add to that, I think the regions for low reward are basically regions where the base policy always does well. So it doesn't really need to give that importance.
So like here's another demonstration of the same visualization where this is like a multi-stage tasks. You have to like pick and place two objects in order. And we see that the diffusion policy again gets stuck while picking up the can, maybe because the alignment was wrong. And then it missed the pick in the end. And then we reset the agent again to start from where it failed and just deployed the Sailor agent from that point. And we actually see that with the test time planning, Sailor was able to like pick the can, and which led to a successful pick. And here again, you could see that when it pick up the object, the reward scores are pretty high. So it is able to like differentiate between like the failed states and the successful states that enable like the test time planning. And here is another attempt at like the diffusion policy, trying to pick up the peg and failing again because it's an OD state maybe. And then we reset reset back to one of the failure states and start like deploy the Sailor again. We actually see that it was able to like pick up the peg in its retry. And in the reward model, again, you could see that you get a pretty high score as soon as you pick up the peg. So the no reward model is actually pretty powerful in like differentiating between the key states or the critical states between the expert and the policy. Now, another like key observation that we made was, okay, we use the same set of, we use the demonstrations right at the start of training. And then for Sailor, we just do like on policy rollouts, update the components and do test time planning. But what happens if we just scale up the diffusion policy data? In a way, like you could actually do this because nowadays a lot of frontier labs are doing it. You just scale up your data collection, hire a lot of people to do it and get a lot of data and train like even more powerful models. So this experiment was trying to study that. If we make the data for diffusion policy by up to 5 to 10x, we could see that a diffusion policy improves for each of the three tasks showed here. However, note that the Sailor agent with the least number of demos was able to like outperform the diffusion policy in this case. So just like scaling up the amount of data isn't enough to close this performance gap. And here is what I would like to talk about, like something very important, that even though you can collect a lot of demonstrations, the agent can still go to the OD states, auto distribution states, due to like covariate shift at test time. And it doesn't know what to do in that state. Now, you could always say that, okay, while collecting the data, because I want to teach the model to recover from mistakes, right? While collecting the data, you can ask the human or the expert who is collecting the data to make a lot of failure cases so that you can maybe collect some instances of that. But it would require like a huge number of data collection, and also like all instances where the agent can fail, which is obviously hard to predict. So even if you collect like recovery data, the agent can still make some mistakes when trained with behavior cloning. So the problem never goes away even when you scale the data. And maybe using some sort of test time planning is like pretty crucial with the learned world model and the reward model to make a better choice in the actions that actually solve the task successfully.
Yeah, Arnav, I have two questions. So what you're showing here is that the behavioral cloning or like this just not non-Sailor, like with a bit more data, it does improve, but it still can't even match Sailor with like a lot less data. But I suppose Sailor itself doesn't benefit from having more examples, does
So
it?
I think it does. We have not plotted it here, but if you give it more examples, it's easier to learn the reward model, and it's also easier to learn a world model around the experts. So if you plot the points for Sailor, it's gonna keep improving. But I don't think we have plotted it in this. But in the previous plots, you can see Sailor improving with the
Oh, I see.
demonstrations.
Yeah, because
yeah. Cool.
Sorry. So the reward model is trained on the negative non-expert data's rollouts, right? So have you done iterative rollout? Have you done iterative Sailor? Like run it like once and then, like especially for a really long horizon task, like run it a couple times and get a new batch and then keep refining the reward model. Like I'm just curious as to whether or not you can continue to get to tasks that are not. Sorry. Well, you answer. I've got a reason for this, but
You wanna go, Arnav?
Yeah. So the first thing, as Web said, like the Sailor actually improves if we increase the number
Sure.
of demonstrations. And one of the reason is that if you see the diffusion policy improves, so you're always starting with a better base policy. So if you train with the same number of interaction budget that you have, the performance goes up. The second way to improve the Sailor agent is always you can increase the interaction data. And in some of the tasks, we actually saw that if we train for maybe like more interaction budget, the performance is
Okay.
still going up. We just kept the budget to like some number of like 200K or 500K in this case. But when you also like train on these tasks for 1 million environment steps, the performance was improving, and on some task which is even close to 1.
Yeah.
Yeah. So, actually, go ahead, Vib. Yeah.
And you mentioned like the fact about the iterative training. I think we're already doing that, where we basically deploy Sailor into the environment, collect a bunch of demos, and I think that's around 10 to 15 trajectories. And we use that and train the world model and the reward model for some steps, and then roll it out, roll the Sailor again, and keep doing that. So I think with the iterative framework,
okay, fair enough. Yeah.
Yeah.
So yeah, not getting anything else. That makes sense.
Yeah.
And I guess because the policy is already because this is improving your base policy, it doesn't matter that the earlier parts of the trajectory get harder for the reward model to distinguish. Okay.
Yeah.
Oh, makes sense.
Right.
That
We
works
always just
nicely.
want the reward model to just be like a direction of local improvement, and that's what matters.
Yeah. I'm also curious about like what are some dimensions you guys you think can push within this paradigm so that you can get it very close to 1? Is it just a lot more compute during inference or what?
Yeah, just let it run.
Yeah, I think if you increase the number of interactions, you can actually, I think in our experiments, we saw like
It
in
might be
these
the next
tasks.
slide, actually.
Is it?
Yeah, you have a slide? There you go.
Yeah. So I think, so the first thing we can do to get the success rate to 1 is obviously give it more number of samples or give it more number of iterations of MPPI. But for some tasks, as like for stack here, it is not able to reach exact 1.0. And I think the limitation there is like the world model missed to capture some edge cases, or the reward model missed to capture some edge cases again. So like to get the success rate to 1, you would need to give it more interaction budget. That is the first thing. And I think that's what we observed. If you give it enough interaction budget with a sufficient number of expert demos, which is like say for stack, I think 15 was good enough. You can see success rate going to almost 1.
Cool.
So to summarize, like you can, to improve the performance, you can, if you have more inference budget, as we see in LLMs, like you can generate a bunch of rollouts, evaluate more things for best of n or any metric, and then pick the one. So here in this plot, we actually show this thing that if you increase the number of samples, because in MPPI, you're generating a bunch of samples to evaluate. If you increase the number of samples, whereas x-axis denotes this thing, the performance actually goes up on most of the tasks. For example, in CAN and round, it actually reaches above 90%. Now, in some tasks right now, maybe it doesn't touch the 100%, which we actually want to have a better system. I feel then you can do more training. You can always improve your world model and the reward model. you can collect more interaction data with the latest policy that you have, do the batch online RL, train it better, and then deploy it again at test time. And that should like improve it. So to summarize, you can always use more budget at train time and test time to improve the performance.
I think also like just using a much stronger world model is gonna boost performance, especially if you wanna do it in the real world.
Did you guys get to test in the real world at all?
Actually not.
Future steps, yeah.
You,
All right.
you sound like one of our nerves reviewers. But yeah, I mean, I don't know. I mean, definitely like we really hope this sort of thing could be useful for a bunch of things in the real world, right? You know, I guess there's maybe some of the kind of obvious things you might want to do for that, like you use something like a VLA as the base policy. You might use something like a Dyno World model or something else as like a good kind of has like good sort of visual features for things. Yeah, I don't know, Vib, Arnav, anything else you think we would do to make it work better in the real world?
So yeah, we have been thinking about this. That's a great question. And of course, we have this awesome algorithm and we want to test it on a real robot to show its applicability. So one of the first thing is like you want to make the training efficient. And to make the training efficient, as Gokul said, like you can always use a much better policy. And as Web mentioned earlier, you can use a pre-trained world model or like better embeddings to start with, so that you don't have to like do a long warm start, which we actually do for training the dreamer. You can actually start with that representation and do some fine tuning with very less collected data. The second thing is test time planning. Of course, we are using a MPPI thing, and we actually like time this out, like how much time does a diffusion policy is taking and how much time is the MPPI planner taking. And we actually saw that the planner doesn't take a lot of time. You can actually bring the time taken by the planner to like half the time the diffusion policy takes. So it's not a lot of overhead, even if you have to do test time planning. And the reason for why MPPI is like pretty fast is because we are doing like planning in the latent space for the world model. And Dreamer has been able to train evaluate very large batches in one go. So one iteration takes very less time. Like everything happens in the batch. So
also, I would like to add that the time taken for MPPI only depends on the iterations because the samples are parallelized across the GPU.
Makes sense.
Yeah. So we have been thinking of this, and because diffusion policy we know has been deployed in the real world, and given that it is just like a bit more overhead, and you can always with more training bring this down, bring the number of iterations down with some tuning and all, and you can just deploy it out. Yeah, we hope something is out soon.
Okay. So you're working on it. Yeah.
Yeah, maybe there's like two other things I think would be maybe kind of important for real world stuff. I feel like one thing would be like, and this was Vib's idea of, you know, once you've learned this whole like search process, right? Like we're doing this kind of thing where you constantly update the base policy, where you kind of like distill things back, right? Let's say for whatever reason you're doing something that's like super real time and you basically cannot actually even do test time planning because of like wall clock time reasons, right? You could just kind of do one kind of final post hoc distillation of the whole thing into the base policy, right? And use that as the thing you deploy. And then, you know, there's been work on, you know, speeding up inference for like, you know, diffusion policies by, I don't know, replacing them with like consistency models or something like this. And that could give you something pretty fast. Another thing is like, yeah, I feel like when you get to sort of things outside of the sort of tasks we had here, maybe things we use something like a VLM as our word function, and kind of use that to kind of use sort of a broader notion of success might be useful. So like, I feel like we're kind of giving maybe like the standard answers here, right? But it's like, you know, you have a more powerful base model, use a more powerful base world model, you kind of have a kind of better class of word functions, right? And then you maybe do some sort of post hoc distillation to make things a little bit faster at testing.
Sure. I mean, diffusion policy is already fairly slow. So like this is a well studied, not at least as well studied, I guess. So
Yeah.
why do you need the more powerful vision and word model? Why, like if I set it up in a like your simulations are of a Franck arm. That's a very precise industrial arm. Like you put it on a white tabletop. Like would you expect this to just work out of the box as is, or is there something else stopping it?
Yeah, that's a good question. I mean, I might expect that if you like, you know, set the scene up really precisely, everything will just work. Like if there's not like,
okay,
but
fair
like,
enough.
Yeah.
So it's got to go back in the same place every time. So that's
Yeah. So,
all right.
but like, what I feel like I'd be kind of worried about, and I said, remember we're kind of trading this like classifier between what the expert does and what the learner does, right? If that classifier starts kind of attends to features that really don't matter, right? This can maybe get you to be penalized for doing something that's actually not that bad, right? So I guess the hope of using something like kind of a better visual kind of set of features, maybe on top of VLM or something, is that you essentially have learned that, okay, roughly speaking, these are the set of things people kind of care about. Like they care about whether objects are inside bolds. They care about like, the relative orientation of certain things. And this kind of like, in some sense, kind of masks out some differences that don't really matter. And you can really just like focus in on the details that do matter.
Mhm.
So like I think maybe for like the task we have here, right? Like, the background doesn't change and other stuff, right? So like, but I could imagine as you sort of want to get this like real, more open world things, kind of filtering out or doing some kind of pre-filtration of what kind of matters is important. Yeah.
Adding to this, Gokul's previous point on like post hoc distillation, I want to also mention that as a fun experiment, we actually tried it out. That after the training, you take out a lot of states from the replay buffer, relabel them with the planner, and just do a large distillation on the base policy. And that was actually able to like make the base policy even much better and closes a gap between the test time planner's performance and the base policy. So if someone wants to really like is constrained by the time of just using the diffusion policy, can also like do that, and it works.
You can think of this like reusing compute during test time, during training time at test time. So you're just asking the planner to solve a bunch of problems which it saw during training time, and then just distilling that back into the diffusion policy, so it already knows the solution to some of the questions.
Yeah.
Sorry. Okay. I also did not ask about this last slide. Why doesn't it lead to reward hacking? Is it just
That's a great
empirically
question.
true, or
Yeah.
do you
I think-
like why not?
The benevolence of the universe. But I mean, it's a good question. I mean, like, I can give you my take, and then let me know if I missed something. Whenever. But I think part of the reason this is happening is because we are doing this sort of residual search. We're only kind of looking in a relatively narrow band around what the base policies actually did, right? Like, I'm fairly confident if you threw in something that was crazy into this, it would like
Okay.
put out just like complete nonsense. But like, I think it's sort of always a solution, right? Like, like when we think about things like RLHF, right? Like you add a KL constraint, so your policy doesn't ever do anything crazy. So the reward model doesn't get tested on something crazy.
Well, actually,
that
this is something that does happen with RLHF, right? This is why you only run it for a few different steps. Otherwise, it does start to reward hack, and it starts to
Yes.
yeah.
Yes, right. But I think a lot of times this happens because in RLHF, a lot of the methods there aren't really good at enforcing the KL constraint. Versus
Okay.
here, we essentially can just like clip the actions, or we can basically say they
I
have
see.
to look like this, right?
Okay.
Like things that look like, for example, like DPO don't actually enforce the KL constraint. So I think you kind of see this drifting over time.
Also, one more point to add here is when we are training the reward model and the critic, we actually have like some notion of uncertainty about if the word model is accurate there and if the reward model is accurate there by using an ensemble of critics, and we add that to the cost function of the MPPI. So we are actually forcing the search to be only in regions where we think the word model and the reward model are accurate. So that might be one of the reasons why it's not reward hacking.
Yeah, that's
makes
a really good.
sense.
Do you have anything to add, Arnav?
Although, we are just using an ensemble and using the epistemic uncertainty. We use that as a penalization constant while planning a test time, so that whatever actions you predict by sampling, it doesn't like allow you to exploit the inaccuracies in the world model and also the reward model. So that is maybe actually helping with reward hacking. And it seems like it is pretty standard because many recent papers that do RL training, like TDMPC, the newer versions of it, and something like even RLPD that did offline RL training, they kind of use an ensemble of reward Q functions to actually like guide the agent to not like explode inaccuracies in the learned networks.
You have a couple more slides after this, right, Anna?
I think we might have just one more. I think this might be the last slide.
So the thing is, when I mentioned about the 3 phases of training a C-worthy sailor, I mentioned 3 points. The first was like the warm start was crucial, and we have also been talking about it. So the first result on the left actually shows what the effect of warm start is. So if we don't do the warm start, we don't get like great performance compared to training with the warm start. And in our case, whatever interaction budget that we had, we used like the 20%, around 20% of that to roll out the pre-train diffusion policy, generate a bunch of data. And that was actually helping with the final performance. The second thing was, I
Actually,
mentioned
can
that for
Can I add like one point on that? Like, I think one thing that I think is actually like was surprising to me in hindsight was that like I feel like a lot of methods, there's always this kind of, you do some offline training and you try them online, right? And there's always this sort of like maybe like dip in performance or something when you like kind of try to do online fine tuning, where it's like catastrophic forgetting, where things kind of fall apart. Like I think even beyond what we did in this paper, I think like it turns out that some of this sort of offline to online stuff turns out just collecting enough data and just fitting your reward model, your critic, and your world model just kind of on this data was sort of enough. And like I feel like it's kind of cool just that the sort of simple thing here actually just like worked pretty well without it, rather than having to do something like kind of complicated. Because like I remember for a while, Viv and Arnav spent a really long time trying to get the avoid the little dip in performance at the beginning, and then eventually we are like, wait, what if we just tried the obvious thing and it worked? So
Yeah, I think to also add to that point, I think one of the reasons why this worked in this particular setup is we just need to make local corrections to the base policy. So if we have a good enough world model and a reward model around the original base policy, we should be able to improve it somewhat in the start itself, and we don't see a dip in performance. And another thing to mention is if you don't warm start like this, but you keep training for longer, you eventually hit the performance of the original. But just in the same amount of interaction budget, it's hard because the performance has dipped and it's slowly starting to improve again.
yeah, that's a good point. It's like basically maybe it doesn't affect the asymptotic performance, but it's like
Yeah.
it just takes way longer because you just don't have a good in distribution world model in some sense to start off with.
Interesting. Makes sense.
So the second thing that I mentioned was like doing a hybrid training when training the world model, like train the world model on the mix of the expert demonstrations and the on policy data rather than just training it on policy data. And this was also like similarly crucial, as you can see in the plot in the middle, where just training the world model with the on policy data, which by which we mean the no hybrid world model, the performance was like pretty bad right at the start in PokeCube. Maybe like didn't lead to like optimal performance in serial. So we saw like both trends in different environments, whereas doing the hybrid training was actually like leading to optimal performance. And this to us also like made sense because suppose if the world model is only trained on an on policy data and by any chance the agent visits the state visited by the expert, it won't be accurate on those states. So even on the good state, it's gonna like perform bad, which will hamper the test time planning and all. So you want the world model to be like good at both the expert visited states and the on policy data.
Yeah, and I think even beyond our experiments, right? I think this has shown up even in like if you guys read the report from like 1X on their world model stuff, I think they also did sort of hybrid training there, and you can do a lot fancier math to justify it, but I think it's basically what Arnav said, right? Where it's like you want to know if you do the good things happen. If you do the wrong thing, bad things happen.
Well, so just partly just like using as much data as you have for the world model makes sense. Although I'm surprised that it makes such a huge difference, because I would expect that the expert really on PokeCube here, because I would kind of expect that the expert would be visiting a lot of the same states, right? Or the on policy data would contain a lot of the same states. Do you have
I think it eventually does, right? But it's a hard exploration problem, right? So it's like at the beginning, you have to know that you can like poke the cube, right? So it's like the benefit of using all this hybrid data, right, is essentially it lets you not have to solve an exploration problem via on policy samples, right? It's like you already know if you went here, this is what's going to happen.
No, makes sense.
I think even here, the same thing might hold true. Like if you just keep training it for longer, you might hit the same asymptotic performance in both the environments. I think in one of the cases, the initial performance was way bad, and in the second case, it's not able to improve at the same rate. So there is definitely like a lot of benefit to hybrid world model fitting.
Do you need to do any weighting or anything like that? Like preserve some amount of the, I don't know, like with these co-training papers that preserve some amount of it for expert data, or do you just treat all samples equally and throw them all together?
It was all equal.
Okay, yeah.
We don't have any weighting because we don't have like any notion of what a good reward looks like.
Yeah. I mean, I think like, I guess, I mean,
because they're all equally valid samples for the world model too, right? So I guess it wouldn't matter.
Exactly.
Yeah.
I could imagine maybe if your world model is like not super powerful, then maybe you want to have it kind of prioritize more recent things in some sense. But we kind of view these world models as sponges, right? Kind of to your point, kind of should just shove whatever we can into them.
Yeah. So I guess, I mean, this is a question that we like to ask, like maybe towards the end of the let's say if you guys have, I don't know, maybe a few more months on this paper, like what would you have squeezed just on this? What would you have done more? Probably 3 months is not enough to get a real robot. That probably is a new paper by itself. But it's 3 more
3
months.
months and 3 months and how much money? It depends on the.
That's true. Well, let's say no money is no object, but just 3 months. Is it just more?
If money is no object, we have no problems. But I get what you're asking.
Yeah.
Yeah.
Arnav, do you want to take it?
Yeah. You can go ahead, Arnav, first. Yeah.
I think one other thing is like, I think it's mostly around like whatever we have discussed in the last hour. And one other thing is like making this training pipeline even more efficient. And that is by using maybe more powerful diffusion policies or using some form of pre-trained representations. Like start with a VJEPA thing, try to use that and see if you can bring the interactions much down. One good thing about this work was that on most like simulation-based RL papers, you see that they do the training in a way that you take one environment step and maybe 1 or 2 agent training steps in general, which is quite feasible for the real world. And we wrote the code in a way that we should be able to deploy this. That's why we did the batch online RL thing. That is, we collect a bunch of demonstrations, maybe like bunch of on-policy data, maybe like 25 or 100 trajectories. Then we first like update our world model and reward model, improve them, and then collect the data again. So maybe the goal was that you should not need more than like 8 to 10 iterations if you are deploying this on the real world. So one of the focus would have been like using these more like good pre-trained representations and bring the interaction data down and make this pipeline even more efficient. The second thing is, as I mentioned earlier, that we are using like test time planning and all. And one line of work is, of course, making that planning efficient by reducing the latency, because it comes with some overhead. And how can we like even engineer it to like bring it down? The third is, for me, it was like we discussed this thing of right now we are training a classifier kind of reward model, but we actually wanted to try something like a VLM or something. And I think the 4.1 paper, which Gokul is also a part of, they actually were able to like deploy something with a mix of diffusion policy, dreamer agent, and a VLM on a real robot. So maybe we can try VLM as a good reward, as another reward model, and with like a similar infra, we should be in a state to actually deploy this. So these are the things that I might try.
Yeah, I think to add to that, I think one of the other things which we need to do before we roll it out in the real world is we need to ensure that when we're collecting on-policy rollouts, we don't mess up very badly. And we can actually reuse the world model and the reward model we have used in order to curtail the exploration there. Because in the real world, you don't want the robot to like hit something or like go into a state which is not really good for the physical robot. So you can design some kind of like a shield around which the exploration is focused, so that you don't break the robot while it's doing on policy rollouts.
Yeah. Those are great answers. Those are like the practical answers. If I could just have, infinite time and money to do things, I feel like one thing that I'm kind of interested in is the following. Like we're doing, tasks here that are, not short horizon, but they're not like the robot does something for like 10 hours, right? And I'm like kind of interested in like, maybe for example, if we use like a different sort of plan or something like a task and motion plan or something that can kind of have natural hierarchy or sort of like handle sort of longer horizon things. I could find that kind of interesting. Another thing I also find, I don't think it matters at the particularly short horizon, but I could imagine mattering at longer horizons, is that like world models generally aren't super good at long horizon prediction. So like, I feel like, another thing I'd want to look into more is like, okay, are there ways to sort of like stabilize kind of longer term predictions from like world models? And then maybe like a third thing I find kind of interesting is like MPPI is this sort of like very fixed algorithm, right? Like it's something kind of hard coded, and we sort of learned every other component. And I think I find kind of interesting, at least from like a kind of theory or algorithm perspective, is like can you in some sense like learn a search algorithm? So like, can you, for example, like learn to, for example, like let's say you did some computation on one of these like threads, essentially these like n different parallel samples. Can I learn to actually not have to redo that computation on other things, right? Think about something like best of n or so like parallel reasoning for LLMs. Like I'm almost curious if you can take some inspiration from that and sort of kind of avoid like kind of repeat computation in some sense. I don't know how to make that like particularly formal or like, precise, but like there's some sense in which I feel like you might be able to essentially reduce the amount of computation the planning process takes by being a little bit smarter than like sampling n different parallel completions completely independently, evaluating them and maybe something kind of in the sampling process. Yeah, I think those are maybe at least on top of my head, what I find kind of interesting.
Yeah, I think on your last point, like I can't remember was it your tweet thread on this paper where you kind of mentioned also the potential of something like this down the road, being able to dynamically allocate the appropriate, let's say, compute. Some tasks maybe, I don't know whether short horizon or versus long horizon is the right way to put it. Some things could be very difficult but very short, perhaps. But it's just like knowing when to put more test time compute to do certain things. I think otherwise if you just arbitrarily, you could be wasting or like under budgeting, right? Depending on the task.
Which is, I think, a really interesting question, right? Because like, okay, let's say we think about like the sort of tabletop-ish manipulation things, right? There's a lot of thing that is just motion through free space where as long as you don't collide with yourself, it's kind of fine. And then there's things where you're doing like kind of contract-rich manipulation, right? Where you're like, let's say you got like the Chris's example, like screwing the thing in or something, right? What I would really hope is essentially you can learn a thing that says that when I'm doing these kind of harder parts of the task, I have to sort of allocate more compute. And what would be really cool is essentially you can do this in a way that does not require kind of pre-specifying the amount, right? Because like, as you get kind of more and more complicated, it's very hard to, have this sort of system where you can just write down exactly how much each different part takes. So I feel like, yeah, kind of doing that sort of adaptive allocation of compute could be kind of interesting. And I could imagine you might be able to do something like relatively simple, right? You could essentially, maybe you have like some sort of reasoning model or something, essentially just say, I want you to do the task well while minimizing the total number of like samples you generate during the planning process of the whole thing, right? And then maybe you can imagine a different states. It says like, okay, only at these states you should reuse more compute. At these states you should have less compute, right? And I feel like a lot of people in LLM land are now thinking about these sort of more kind of efficient reasoning things, and a lot of them kind of boil down to something like this, where you say, I want to do the task, but minimize the number of like tokens I generate or something like that.
Does the reward model help you there because you can tell like that it needs more compute or less compute, something like that? I guess we just lost Gokul.
Yeah, I think the reward model can be really useful there because you can see like the delta so when you're doing MPPI planning, you can see how fast you're improving in the reward model, which can give you like a sense of how hard or easy is it to achieve like an objective. And you also have like these uncertainty estimates, which might be able to, like if you have more uncertainty, you might want to search longer.
Yeah, that's right. And I think reward model would be nice because in a way you want the agent to recover from mistakes. In most scenarios, mistakes happen because the agent is in a state that it has not seen before. And because of that, it goes into maybe the new state it might not have seen before. And there you might use the reward model to know if it's a bad state. And there you should maybe allocate more compute or test time budget to actually like do a better search and look for a way to like go to a state which is more expert-like and solve the task from there.
Makes sense. So you do see it in practice. So like when it's performing worse, like the reward is worse, it is a valuable signal that I need more, that more samples will help. Okay, cool.
Yes.
Yeah.
I don't know whether Gokul is going to hop in on, but I guess do you guys have any more thing you want to add to the paper? Otherwise, there's a typical last question we'd like to ask. But anything else you guys want to add? Maybe there's one
thing I want to mention that the importance of test time planning, because we just like talked about it, and we did this another fun experiment where instead of doing the test time search, what happens if you train a residual actor within the world model? So if you see the Dreamer world model, it trains an actor by doing on policy rollouts in the world model. So we also like try to do that you have the same base actions, and now you are doing like learning an actor with your trained reward model and the critic. And what's the impact of it on performance? And we actually saw that it was actually not doing as great as using the test time planning. It was actually worse. It was doing better than the diffusion policy, but there was still some gap with the performance of Sailor, like which shows the importance of doing like test time planning to still like improve. And we have been seeing this in like large models also, like test time planning and more inference time budget actually brings in a lot. So yeah.
Yeah. I think another point I would like to add is so when you're learning like a discriminator for the reward, if you have like a very powerful policy which you're fine tuning on that reward, the policy can actually exploit a lot of holes in the discriminator initially when it's not good. And this setup actually allows you to not get into that by focusing the MPPI search on a very narrow region around the export, around the base policy. So you will see less and less amount of tuning required in the discriminator in this setup. And we actually tried training like these off policy algorithms out there on a diffusion model with a discriminator, and it's really really hard to tune the discriminator to actually work if you have a very very powerful actor.
Yeah, makes
Another
sense.
thing I would like to add is like we also tried to build a model-free baseline where we took the diffusion policy optimization, the DPPO paper, and instead of using the ground truth rewards, we use the same discriminator, that same way of learning a discriminator that we used for Sailor, and we just wanted to study how much does like interacting or like doing planning with the world model saves that. And we actually found that with the same budget, or even like 5x more environment budget, the DPPO version of Inversehile was not able to match the performance. So using this sort of framework with like a learn world model and the reward model was actually pretty powerful in our experiments.
Yeah, thanks. Gokul, yeah, we're about to wrap up here. We're just asking the guys any like final couple of things you want to say about the paper.
Yeah. Let me think. Okay, this might be like a little in the weeds, but one thing I think maybe a little, and maybe Arnav everybody said this, but one thing I think it's a little bit sort of underappreciated, about I think the idea of doing test time planning is sort of thinking about like, why is it useful, right? And I guess the more I thought about it, I think there's maybe one or two reasons why it really makes sense. I think one is that for a policy to do well, right? Assuming it doesn't generalize super well, right? Essentially, it needs to have seen something at train time of like how to behave in a situation, right? So in some sense, right, like if you are training a policy, you kind of have to deal with a bunch of things. So you kind of have to train on kind of every state you could end up in. Versus at like test time, right? I feel like you only have to deal with the state you're actually in, right? So like in some sense, like even on like terms of like compute scaling, I would expect things that kind of look like this flavor of learning to search to sort of scale better, because I only have to like pay for what I actually see, not all states I could like possibly see, right? So I think that's why I kind of believe this sort of direction is like generally kind of powerful. The other reason I think this sort of flavor of things is really nice is that like part of what we're doing here, right, is we're learning a couple of reusable components, right? We're learning a world model, a reward model, a critic, right? And we're combining them, right? And in some sense, when you can take a big problem and you can sort of factorize it into smaller parts, and you can learn each of the parts well and kind of faithfully recombine them in some sense, you're kind of like trading like compute for data, in the sense that you're essentially saying that I need kind of less data to like kind of learn, rather than learning this whole big thing at once in like one monolithic part. So I also think like in terms of the kind of amount of data it kind of takes to train these things, I would kind of expect this to not take too much compared to, let's say, like direct kind of policy learning. So I think both in terms of like compute scaling and in terms of data scaling, I really like this sort of flavor of approach, right? Like compute scaling, again, I think is really because like you only have to deal with the states you see at test time, and data scaling is better, I think, because you essentially only have to be able to kind of tell what is good and predict future outcomes, rather than having to be able to generate good behavior from scratch, which is sometimes a harder problem and should require more data. So like kind of like longer term, I expect this to be a thing where we're going to see more and more kind of approaches, both on real robots and in other domains, that sort of kind of look like this. So I think it's sort of the kind of the compute and data optimal way of scaling a lot of things.
It's a very compelling argument, I think.
Thanks. I came up with it while I was waiting for my internet to reconnect.
Yeah. You use some of your inference computer is good.
Exactly.
Yeah, okay. Well, thank you so much for making the time, and I think this is a very, very interesting paper to me. Yeah, I mean, anyway, Chris and I usually would do afterthoughts after this, but maybe just to really wrap up the whole thing. This is a question that we always ask. Are there any like papers that you guys come across recently you want to give a shout out to? Doesn't have to be directly related to Sailor, but anything that kind of pique your interest. So yeah, we can also read that paper, or maybe get those authors to come on as well. And any shout out. Yeah.
I mean, you should read the forewarned paper if you haven't read it already. Not a shameless plug. You don't have to have me twice, but I think it was really cool seeing maybe it's not the exact same idea as what we did here. I think forewarned is really about policy steering in the sense that you're trying to select like a mode rather than like be correct behavior when the base policy never does the right thing in the first place. But I think there's sort of there's some really beautiful ideas there and some deep connection to things like safety that I think are really cool. So yeah, that might be a fun one to read. If there was a paper you shared recently that I liked, something about diffusion steering, right?
Oh yeah. So I want to talk about two papers. So one is diffusion steering, which is from Berkeley. So they basically have like this prior. So like diffusion models require a prior, right? So they just learn a policy in the prior space to guide the diffusion model. So you can think of it as diffusion model mapping a N01 noise into a trajectory. So what if you can, instead of sampling randomly from N01, sample from a learned policy to get the desired outcome? And I think that is a very interesting idea, because then you can have like very, very long, very, very large diffusion models and never require to actually touch the model weights, and then like just guide it from like the prior space to get to better results. And the other paper which I really liked recently was mean flows, which is basically getting to like a single function evaluation inference for diffusion models, where they, instead of training like the denoising step, they just train the whole flow together. And that's another paper which I think is very important to the diffusion community and also like the flow community. Yeah.
Yeah. And maybe like one thing I really like in particular about the first paper Vip mentioned is that I'm not sure this is very true in theory, but at least on like a vibes level, right? If I'm basically putting like zero mean Gaussian noise into a policy and getting things out, right? When I'm searching for this sort of policy that is a little bit better, like it's simply doing mode selection, right? If I essentially say don't ever pick anything that's like super unlikely under a Gaussian, aka like don't ever pick a thing in the latent space that's like super large and norm, I can effectively say don't ever generate something I didn't see in my training data. And I think this is like maybe like a really useful like building block for a lot of sort of like things you might want to do. Like maybe this is useful for certain like safety things, maybe this is useful for certain like OOD things. I like that paper a lot. I think it's an underappreciated idea. Yeah, and the mean flows paper was of course excellent. Yeah, what about you, Arnav?
There was this paper, I think, from Sharon's group, which was about like learning a guidance to improve the
Oh, yeah.
diffusion models. And what they did was like in the actions at a particular time t in the diffusion model, they actually have a trained world model, like a dyno world model. They do the planning, and with some form of like distance metric, they figure out which actions are good, and then like use that gradient as the guidance term to improve, to refine the actions at the next step in the diffusion process. That was pretty cool.
So
Yeah.
what's the paper called again, roughly? Learning what? I found the article that you guys talk about, but what was it?
Find
Okay.
it. I don't fully remember the name, but I can share it with you.
Okay.
Sharon's paper, it's called a Dyna Guide.
Oh, that, yeah.
Dyna.
It's cool. Like I think we're kind of seeing like a bunch of these papers that are like kind of exploring essentially different versions of like ways to do policy steering, right? Like I think that like, which I think is like a super interesting question, right? So there's like the version that we did was essentially take a base action and yeah, there you go. Thanks, Arnav. One version is you basically like take a base and yeah, there's the steering your diffusion policy.
And
Yeah,
this is the mean
and there's
flow,
mean
right?
flow.
Okay,
Perfect.
cool.
You've done. You made their whole.
Gosh, man,
good
my
work.
weekend is burned again. Just this paper. Good gosh. Okay, cool. But that's great.
But like, I think what's really interesting about these things, right, is like they're all, I think, trying to solve a similar problem, and there's like little details that are different, right? Like for forewarn, we essentially did like clustering a latent space. Basically, picked one of the clusters because it was like a very much like mode selection, right? Here we basically said I'm going to take something and I'm going to like kind of just search in like a tube around the action. That's sort of like like we're doing. I think we're actually doing things like an ender vector, like action space, right? So it's literally like a tube. And we're trying to say like, does that kind of make things locally better? And then I think for things like like diffusion steering, they're instead saying like, okay, what if I optimize the thing I pass into the diffusion model in the first place? And then I think DynaGuide is instead basically, it's not exactly like classifier-based guidance, but it's kind of similar thing in the sense that you're essentially during the actual denoising process, trying to use a world model to basically kind of guide it towards maybe some outcome you want. So I think all of these things are basically exploring different ways of like kind of trying to take some sort of pre-trained policy and make it better. I think maybe what is sort of different about Sailor, I think, is that maybe we were trying to do it without any sort of extra reward information and kind of make as few assumptions as possible. But kind of beyond that, I could imagine you combine, let's say, like a learned discriminator with like all these other things. And it's very interesting to think about, like, you know, it's very cool to see like the community kind of had all these different ideas kind of show up around at the same time. And it's kind of cool. I also have another friend who wrote a paper on policy steering that I don't remember right now on top of my head what the title is, but it was with Jeff Schneider here at CMU. So I'll link that to you guys so you can mention in the video description or something.
Sure. Sounds
Cool,
good.
cool. All right. Yeah, this is maybe one of the longer episode with that. But
There's a
no,
lot
no,
of stuff to cover.
it's good, man. I think it's great discussion. I think well, yeah, like I said, I mean, me and Chris will do afterthought, and you guys can tune into that one. But yeah, thank you so much for your time, and I felt I really learned a lot. Clearly, a lot of reading to catch up on this weekend.
Yeah, thank you guys. Really interesting stuff.
Yeah.
Awesome.
Yeah. We should ask, were there any questions you had that we didn't answer, or like things that like were kind of okay?
Yeah, I think we got quite a lot, and and I think Arnav's actual presentation. Usually we ask a fair bit even from the get-go, but I think Arnav's presentation was very
Very
covered all
thorough,
the grounds. Anyway,
A lot of information.
before I ask the question, yeah, the next slide cover it. So okay,
Yeah.
I'll just shut up and let Arnav go. Yeah, so it's all good. Yeah, but yeah. Anyway, thank you so much for your time. Yeah, looking forward to the next one.
Yeah,
Yeah,
thank you for inviting this.
Yeah, thanks for inviting us. Every now and then I'll post something on Twitter and it's like I'm like screaming into the void, and it's nice when the void like sends you an email. So glad that worked out, and yeah, thanks,
it's
really
good.
appreciate it, and yeah, let us know when the episode is out.
Okay,
Yeah.
cool. All right,
Thanks for having us here. Yeah.
Yeah.
Hopefully this is on the real robot soon.
Great.
Hey, dude. What have you learned, Chris?
Quite a lot. That's a whole lot going on in that paper. It's very interesting, really cool discussion. Yeah, I really like the approach to test time compute, reward function learning, iterative improvement. It seems like there's a lot there. It seems like I particularly think that a lot of this, like, it combines it handles a lot of I think the weaknesses of these world models really well. I am pretty excited about anything to do with reward learning these days. I think it seems like a good way of getting models to really improve. And yeah, what did you think?
Yeah, I mean, I really like it. I think that hopefully, I don't know, maybe through this episode, more people will find out about this. Like, so I think maybe because they didn't do it on a real robot demonstration this time, and these days, like real
rare,
robot
yeah.
demo just on Twitter just go further. But then I can't remember when I saw the tweet thread. I thought there was something there. That's why I reached out. But yeah, I mean, it's a great episode. I thought I learned a lot.
Yeah, I learned a ton.
I think like they say, like each of these component, whether the world model or the rework model,
And the test time.
at test time will it will just improve. They can take something like Genie 3, fine tune on it, let's say, or there could be use like a VLM and swap out and maybe better reward learning. But it's I think it makes a lot of sense that like it can do better than like just straight up more data, but only like naive way of just doing diffusion policy.
But it still scales, it still benefits from more data, right? So, which is the other thing, like a lot of these, I really like these sort of, it's almost planning inspired and like test time compute, right? Meaning basically planning, right? But it's doing that in a latent space. It's using a planning algorithm that's a relatively like a very general purpose planning algorithm in MPPI, but it's able to, like, I think Gokul did a very good job at the end, like arguing for like why test time compute makes so much sense for robotics.
Yeah, especially robotics, right? I mean, you cannot afford to try things out in the real world.
Yeah.
And then you break things and whatnot, right? And so being able to just imagine scenarios and then like inform your planner and then go execute it. So you can do some recovery.
Yeah, it's particularly interesting because like the world model and the way that they've structured it, like usually I think you can end up imagining like really divergent scenarios that won't happen, or places where the dynamics aren't going to be well supported for the robots and maybe aren't very useful. But like their structure allows it to be very focused. right? That's the point
I
that
think so.
they're making over and over again, and that I think like it's very compelling. I really hope to see how it works on a
Yeah.
real robot. Have high hopes for it doing well.
Yeah.
Yeah.
In fact, one curious, maybe in the next paper they'll
Yeah.
won't train the world model from scratch. But my hunch is that there's some benefit to training the world model from scratch themselves also. I don't know. Maybe TBD on that one. Like, because some of the crazy world model are so good.
Yeah.
like Genie 3, just like, oh gosh, like I just woke up a few hours ago and I saw Genie 3.
Oh, the Genies.
Yeah, I mean, you know this is coming, but when it actually show up, and then okay,
It still it still
Yeah.
surprises you when it's like, when it works. Well, I think, there's you could do a whole discussion on Genie though, but like, I was so impressed that it managed to nail temporal consistency as well as it did for like minutes. Of
yeah,
moving
look away,
around.
come back, the pain is
Yeah.
still there. Like, the consistency,
Yeah.
it's something that you have not really seen in prior world models. But
Right.
anyway, yeah.
And it just comes from data, and it's like one of these last things. Every time, like, I don't know if transformers can really handle that purely with data. It's like
Yeah.
always like turns out that yes they can. So that's, I don't know. That's impressive.
Yeah, so I think robotics can bootstrap a lot more with like, things that's happening in the like Genie 3 and
Yeah.
and then take those and then so we
Yeah.
we have to start from scratch every time,
Right.
yeah. Anyway,
But they are fine tuning it. So I think that like what I always wonder with these things is whether or not like a pre-trained model can get like really granular stuff. Like, I don't know,
Oh,
like
yes.
picking this up between my two fingers, right? Like stuff like that. Like, and like maybe not, right? But like the fact that it improves with their data as well means that they're not bounded by like if they use Genie 3, whatever its weaknesses may be, right? So yeah, I don't know. I thought it was really cool. Really cool stuff.
Cool. Yeah.
Yeah.
All right, sounds good. And those few papers, maybe we should chat. But
Yeah, there's
get
like
those
5
authors
papers
out
that they threw out at the end there. Yeah,
got 3 papers to reach out to already.
Right.
All right, sounds
Cool.
good. All right, till next time, Chris. We'll do it again
see you later.
soon. All right, ciao. Bye.